Welcome to section 10-3, Vectors in Space. Here we're going to be looking at three-dimensional vectors. At the end of this section, we should be able to answer these questions. How do we draw a three-dimensional vector? How do we find displacement vectors? How do we find the length, magnitude, and absolute value of three-dimensional vectors? And finally, how do we find position vectors for points located a proportional distance between two other points? First of all, let's talk about how three-dimensional space is organized. We take the xy plane, the yz plane, and xz plane and divide space into 8 regions called octants. The region in which all 3 variables are positive, so when x and y and z are all positive, is called the first octant. The other octants aren't usually named. Here we use the symbols I, j, and introduce the symbol k for the third dimension. They're used for the unit vectors in the x, y, and z directions respectively, as you can see here in our diagram. I is the unit vector along the x-axis, j is the unit vector along the y-axis, and k is our unit vector along the z-axis. Notice how x and y now form the floor of our three-dimensional space, and z is our vertical direction. Here's an example of how to draw a three-dimensional vector, given its horizontal, vertical, and y coordinates. Before we can actually draw this sketch of a position vector, 3i, 5j, 7k, we need to add our third dimension to our two-dimensional graph. So, the way we do that is we take, from the origin, we draw a line about 45 degrees out from the origin down into the fourth quadrant. And that's going to be, we're going to label that as my x-axis. So this will be x. Our horizontal line is now going to be y, and our vertical line straight up will be the z-axis. So we'll take those components, 3, 5, and 7, and we're going to step along each of those axes the appropriate distance. 3i would be 3 steps along the x-axis. So we will mark 1, 2, 3 steps down. And then we go 5 steps along the y-axis. So 1, 2, 3, 4, 5. And up 7 steps along the z-axis. 1, 2, 3, 4, 5, 6, 7. So we have these 3 points along each of the axes. And what we're going to do is we're going to use those to help us draw a three-dimensional box. From the x point on the x-axis, I'm going to move in the y and the z directions, 5 units and 7 units. So we go 1, 2, 3, 4, 5, and we go up from that same point 7 units. So 1, 2, 3, 4, 5, 6, 7. Now I'm going to do the same thing from the y coordinate. I'm going to go up 7 units. 1, 2, 3, 4, 5, 6, 7. And I'm going to move in the x-axis direction 3 units. So 1, 2, 3. And I end up at that same point. Now what I've done is I've created the opportunity to draw a box. I'm going to take these points where I've moved off of the axes, and I'm also going to take one more point. I'm going to take the point I drew up here and move across 5 units. 1, 2, 3, 4, 5. Now if you look, I've actually created a couple of parallelograms here. That lie on top of each other. And if I draw lines down from each of the vertices, I've created a box. To find the actual vector, I could trace my component information along any of these edges and see where I end up. So let's say I start at the origin, and if I move out 3 units along the x-axis, 5 units along the y direction, and up 7 units, I end up here at the top of my box. And since I started at the origin and ended at that point, that would be my vector, my position vector for point P. So that black vector is my position vector. The coordinates of that point would be the amount of movement I had along each axis. So we just read that right off of the vector P. So my coordinates for point P are 3, 5, 7. Now to find the length, we're going to take a Pythagorean approach and use that Pythagorean property where the distances would be the square root of the coordinates, the sum of the coordinates squared. So that would be 9 plus 25 plus 49 square rooted. So that's 34 plus 49, 83. The square root of 83 would be the distance or the length or the magnitude or the absolute value of vector P. Here's another example. Find the displacement vector from point A to point B, where A is 8, 2, 13, and B is 3, 10, 4. Well, to find our displacement vector, we simply have to calculate the amount of movement we needed to arrive at our destination in each of the 3 directions. So I started at 8 and ended up at 3, so my x information is 3 minus 8, which is negative 5. And then I went from 2 to 10, so I traveled 8 units in the positive y direction. And then I started at 13 and ended at 4. So 4 minus 13 means I traveled negative 9 units in the z direction. So my displacement vector then would be negative 5i plus 8j minus 9k. So to find the distance, I need to apply my Pythagorean. In fact, I'm not just going to apply the Pythagorean property, I'm going to apply the super Pythagorean property. And that distance would be my negative 5 squared plus my 8 squared plus my negative 9 squared, all take the square root. So we can see that my displacement vector was negative 5i plus 8j minus 9k. And that distance turns out to be the square root of 170. All right. Finally, let's find the position vector to the point 70% of the way from point A, 8, 2, 13, to point B, 3, 10, 4, in the last example. So again, if we're going to find that vector that's partially along the path between A and B, we're going to take the same approach we took in the last section, where we figure out where point A is. So 8, 2, 13, let's say point A is right around here. And point B, 3, 10, 4, let's say point B is there. So point A and point B. And we want to find a point, the position vector to a point that's 70% of the way between A and B. So maybe like right around here. We'll call that C. Okay. And what we're trying to find is the vector from the origin to C. So OC, we'll call it that. Right. Now to find OC, we need to recognize that OC can actually be written as the sum of two other vectors. A vector from the origin up to A plus a vector from A to C. So OC could actually be written as OA plus AC, where AC is 70% of AB. All right, well, AB we said was negative 5I plus 8J minus 9K. So that turns out to be negative 3.5I plus 5.6J minus 6.3K. So there's our vector AC. And we need to add that to the position vector OA. OA is simply the vector 8I plus 2J plus 13K. So if we're going to add those two vectors together, OA plus AC, that's going to be negative 3.5 plus 8, or 4.5I, and then 2J plus 5.6J, or 7.6J, and finally 13K plus a negative 6.3K, which would be 6.7K. And that would be my vector OC, the position vector, to that point 70% of the way between point A and point B. So 4.5I plus 7.6J plus 6.7K. And there it is. And the coordinates would just be those three values. So 4.5, 7.6, comma 6.7. All right, let's recap. How do we draw a three-dimensional vector? Well, we take the information we're given from the position vector, and we move along each axis the appropriate distance from each of those points. We then move in the directions that we haven't moved yet. So if I've already moved along the x-axis, I then move in the y and the z direction. And if I've already moved along the z-axis, I move along the x and the y. And if I've moved along the y-axis, I move along the z and the x direction. And then finally, I find my last point by taking either of these 2 points and moving either horizontally or along the x-axis. I then connect all my points. How do we find displacement vectors? Displacement vectors are found by subtracting the starting point from the end point. How do we find the length, magnitude, or absolute value of the three-dimensional vectors? We apply the super Pythagorean theorem, the square root of the sum of the x, y, and z distances squared. How do we find position vectors for points located at a proportional distance between two other points? Well, we use the strategy of creating a resultant vector by combining the position vector to the beginning point of our displacement vector and adding to that the proportional piece of the displacement vector.